My name is Chris Dorr, and I am currently in the process of obtaining my master's degree in Spatial Information Science and Engineering here at the University of Maine. Prior to my arrival here, I obtained my bachelor's degree in geography from the University of California at Santa Barbara. In my time at the University of Maine, I have found the Spatial Information Science and Engineering program to be well suited to both my backgrounds in geography and computer science, as well as my current research goals. For the purposes of this presentation, I would like to briefly detail one of my current research focuses on decentralized sensor networks. Sensor networks have a wide range of applications and come in many forms. Usually these sensor networks measure or observe physical or environmental variables such as sound, temperature, pressure, and motion. There are applications in both the military, industrial, and civilian arenas, and these networks can be either wired or wireless, centralized or decentralized, and the agents can be mobile or fixed. Unlike in a typical centralized system, decentralized agents operate autonomously. This allows the network to operate under conditions which might impair a centralized system, suiting it well to disaster or emergency response and recovery. Advantages of a decentralized wireless sensor network include the fact that they operate unattended, can withstand harsh environments, and have dynamic network topology. This means that the network can cope well with localized node or network failures, node capacity is easily scalable, and nodes are often mobile. Disadvantages of these networks, however, include the fact that node power supply is limited, and communication success depends heavily on many environmental and network factors. They can also be somewhat less efficient than centralized systems, as there's no direct way of selecting agents out of the field. While I was in Santa Barbara my senior year, I was fortunate enough to work on a paper with a professor. The concept was decentralized time geography for ad hoc collaborative planning. We wanted to introduce the notion of decentralized time geography, which differs from traditional time geographic framework by taking into account limited local knowledge of agents in a decentralized network. This allows agents to perform a space-time analysis within a geographic time framework that represents local knowledge in a distributed environment, as well as requiring ad hoc coordination for actions between agents in a physical space. Agents in this network exist in some environment. There's no centralized communication, and little global knowledge is known among the individual agents. The agents can, however, communicate in an ad hoc, peer-to-peer manner. Each agent, therefore, has easy access to local knowledge and the capacity to send or receive knowledge from other nearby agents. The example scenario we developed this project to respond to is as follows. A major accident has happened at an industrial site, leading to the spread of chemicals into the surrounding environment. In order to take measurements of several critical variables, a number of agents with different sensor types are needed at the site within a specified time frame. There is no centralized command center, so the agents must collaborate to clean up the spill within the critical time frame. Questions we wanted to answer included the following. How many agents are needed, and how many can be expected at the site by the upper time limit? How large must the search radius for help be to get those agents together at the site? And how difficult is it to reach agents within the search radius? The solution was to implement an agent-based simulation, which would mimic much of the behavior described in the scenario. The results were somewhat surprising. Success in much scenarios depended on many factors. The time frame allowed for response, agent speed and communication radius, the density of agents in the field as well as their types, the density of obstacles between the agents and the goal, and agent behaviors were all very critical. In the future, there are many things that I would like to extend on this simulation. Accidents are, in some cases, predictable. Very few devices or components are 100% fail-safe, and there exist many methods for reasoning about uncertainty. By making inferences about known failure rates and consequences of a failure, agents can more intelligently position themselves in the field. This thereby creates a greater chance that all necessary agents will be nearby in case of a failure or accident needing immediate response. Agent navigation and communication mechanisms are key to successful collaboration and response. The methods implemented in the initial simulation were somewhat limited and could certainly be improved. Decentralized wireless sensor networks, in conclusion, can provide novel solutions to many otherwise common centralized systems. Applications include search and rescue, environmental analyses, emergency response, transportation analyses, and even mobile location-based gaming. With that, I would like to thank you for your time, and I appreciate you listening.